AP Calculus AB, Unit 8, Day 1. So we're going to talk about area and how it relates to calculus. All right, so let's see. So the Greeks are, we owe a lot to them for geometry, and there's a lot of different approaches to figuring out the area of, say, like a circle. One way to think about it is it takes 3.14 squares, like this square, to fill the circle. And so you could think of the area as, and that 3.14 is pi r squared. And I don't know if you ever thought about it like this, but thinking about it as if like r squared is the area of a square with sides equal to the radius. Because that's one way to think about it. We can fit that many squares into this area. The overlapping stuff has to be cut off. I mean, you can imagine a good fit. 1, 2, 3, 4, but not quite. So, yeah. We could cut it up other ways, like a pizza. Cut up like pizza. And then if we do that, here's something interesting we could do. We could reconfigure the pieces, the slices, over here. So these are all the same slices that are here, but I put them kind of side by side. Now, if we were to look at this, we could say, well, this is kind of like, if we cut this piece off and we stick it over here, okay, we put that over there, it's kind of like, it's close to a rectangle, right? I mean, you see that? I mean, it's pretty close to a rectangle. So let's think of it that way. So area of a rectangle is length times width, or base times height. So what's the height of the circle? I'd say is about r, right? This is right here. That is the radius, right? And then the base or the length would be like this. And I would say, well, it's about half of the circumference, because half the circumference is there for the 8 slices, and half the circumference is here for the 8 slices. So this is kind of like halfway around the circle, which would be the circumference, is like half the circumference, half of 2 pi r. So that would be about pi, right? Or, 1/2. 2 pi r. 2 pi r. So it'd be about pi r. So I'm going to say that the base or the length is pi r and the height is r. And if you multiply these together, you get pi r squared. Huh, interesting. So it's just kind of good to start to think about how to find area by cutting it up in different shapes. And maybe even comparing it to shapes that aren't perfect. Now, here's the interesting thing. If we were to cut this up into like 100 slices and reposition them, you'd start to not even be able to tell the bumps here. The bumps would become so tiny that it'd start to look like a straight line. I mean, it would start to really, a million slices, you wouldn't be able to tell. It'd look like a perfect rectangle. So, kind of interesting. Okay, so to find the area of a shape, we could slice it into pieces. If sliced into more pieces, it becomes closer to the actual answer. Okay, smaller pieces, thinner pieces, you could fit them in better. First semester, we dealt with slope all semester long, and that would be, like the slope between 2 points. Well, the slope, the actual slope, but we could estimate it, right? And if we move those pieces, those two points closer and closer together, it got better and better. So now instead of moving 2 points, we're thinking of like slices of area of a region. And the more slices we do, the smaller the slices, the better the estimate. Kind of like the closer we made these points, the better the estimate. The smaller and more slices we do, the better the estimate. So now we're going to be putting them back together and adding them all up, accumulating them. So let's kind of explore this idea some more. So finding the area under a curve. Were these methods created or discovered? Like, did someone make, I don't know, was it kind of always there and we figured it out? Or did we just, someone just made it? So Newton is responsible for much of what we use in calculus. And so let's see if we can take sort of the approach of trying to figure something out, something new that hasn't been discovered yet. So if we were going to do that, if we had some ideas of how we thought we might do it, or we just wanted to try and like play around with it, probably want to start with a really simple case. Also a case that would be easy to confirm. So let's see if we can figure out how to find the area instead of just any curve, which we are going to be doing, the area under curve. That's sort of our goal right now for any kind of function. But let's start with a specific function that's really simple, a line. Okay, so here's a line, just an example line, y equals x plus 2. And we want to find the area between 2 points, starting at -1, and then going to any point x. How could we find the area? Could we come up with a formula or something like that? Okay. So the coordinates here would be -1. If I plug 1 in here, I get a -1 in there, I get +1. And then if I plug x in, I get x plus 2 for the y value. So probably use those. So first of all, let's just figure out what is the answer to this. What is, this is a trapezoid, right? Kind of sideways trapezoid, exactly two parallel sides. Other sides aren't parallel. Otherwise, it becomes a parallelogram. And how do we find the area of a trapezoid? I'm just going to draw a generic one here. Now, some of you guys may have memorized the formula for the area of a trapezoid at one point, and you probably have forgotten it now. You're like, I have no clue. So I want you to take a better approach here, so you don't have to just memorize some new formula, because we really want to avoid as much memorization as possible. If you have a trapezoid, it has two parallel sides, right? We call those the bases. You might call them base 1, base 2. Okay? The distance between them is the height of the trapezoid. All these things are involved in finding the area. But what I want to do is I want to find the midpoint of this side. So it's exactly in the middle, and the midpoint of this side. So it's exactly in the middle there, and connect them with a line. If you do that, that's called the median of a trapezoid. There's medians for other shapes too that are kind of similar ideas. It just connects the two of those. Now, some of the cool things about this is it is also parallel to those sides. And the length of it is actually just the average of the two bases, which is kind of cool. If you just add them up and divide by 2, you get the average of the bases, and that is the length of that kind of in-between base. Now check this out. If we draw a straight line here, and we cut this piece off and we stick it up here, forms a nice vertical line. And we do the same thing over here. We cut this piece and we stick it up there. We actually have a rectangle now. The area of a trapezoid really is just, so by the way, this is a trapezoid, right? The area of a trapezoid is really just the area of a rectangle. Okay? It is the area of a rectangle if you move things around. It's just base times height. But what is the base? The height is the height. What's the base? Well, the distance along that side there, when we create this little rectangle out of chopping those two pieces off, is the median, which is the average of the bases. So the base is the average of the bases. Add them up, divide by 2, multiply by the height. That's your formula. That is your trapezoid formula. Now, you may have memorized it like this, like 1/2 I don't know, b1 plus b2 times h. I kind of like this. It's base times height. What's the base? It's the two bases combined together. You just average them. That's it. It's a rectangle, base times height, average of the bases times height. That's it. Hopefully you can remember that longer now than whatever formula I memorized a couple years ago. Okay, now in our specific example here, the bases are vertical. A lot of times we like to think of the bases as being flat, and we think of our trapezoids as going, the two parallel sides are horizontal, but here they're vertical. And we're going to deal with a lot of kind of vertically sideways oriented trapezoids this semester, not just today. So what is this base right here? This base right here is the y value. It's 1. And what's this base right here? It's the y value. It's x plus 2. So it's going to be, let's see. Let me just make sure we're doing this right. It's going to be x plus 2 plus 1 divided by 2, right? That's the average of the bases, times the height. This is the height. The height here is going to be whatever x value we're at minus that x coordinate, which we're saying is negative 1. It's going to be x minus minus 1. So we're going to get x plus 3 over 2 times x plus 1. We could multiply these all out. Let's see, we get 1/2 x squared plus 3x, 4x plus 3. And so finally the area would be 1/2 x squared plus 2x plus 3/2 for this problem, for that line. If you want to find the area of this line, start at -1 to any x value. Here's the formula that'll give it to you. Now, we don't have to do this for every shape. So we've done this. We figured out, we haven't done any of the calculus yet, right? All we've done is like, well, how do you find the area? How do you get a formula for the area? All geometry and algebra so far. But say you're Newton and you try this and then you're like, oh, I don't know. What happens if we like take the derivative of this, So if we take the derivative, let's just see what happens. He's just trying different things. We take the derivative of the area formula. What do we get? We get x, right? The 2 goes in front, plus 2, and then 3/2 is 0. So this is what we get for the derivative. Is that special at all? What? It's equal to the equation of the line that we're trying to find the area underneath? Is that just a coincidence? I don't know. Let's try another one. And try another one. And every time we get the equation of the original function. Groundbreaking. I mean, seriously, this is a big deal. In general, the derivative of the area under a curve will give you the equation of the curve. That's what happens. It's crazy. Now that we know that, and our real goal is to find the area formulas under these curves without having to do all this crazy stuff. If we know now that the derivative of that area formula, which we don't have yet, equals the original function, can we look at the original function and ask ourselves, what would you take the derivative of to get that? Could we kind of like undo the derivative and get the equation for the area under a curve? Because that's what we're going to be doing a lot of. So let's keep investigating this idea. So it said, let's see, if the curve is y equals x squared, we'll start making it a little more interesting. That's a parabola. Let's just draw a picture just for fun. So it's a really basic parabola, right? Y equals x squared. And let's say, and so what we've discovered as the derivative of the area underneath it is going to equal the original function, which is x squared. Okay, which means that the area formula, how could we work it back? Well, how would you undo it? What would give you x squared if you took the derivative? You got to think, well, it's a power rule, right? Where we would have multiplied in front and then decreased it by 1. So let's do everything backwards. Let's increase the power by 1 and divide by the new exponent. Check it. If you take the derivative of this, do you get x squared? Sure do. Multiply the 3 in front, cancels the 3 on the bottom, decrease it by 1, gives you x squared. Perfect. So if you're undoing derivatives, you need to just do everything in opposite form. Usually you multiply this in front, decrease by 1. Well, now we're going to increase by 1 and divide after the fact. Everything is opposite. We call this right here the antiderivative. It's the derivative backwards. We also refer to it as the integral of x squared. Okay? So, let's say if you plug in 3, it's going to give you, now by the way, this formula is going to give you the area from 0 to whatever x value you plug into it. Okay, so let's say if you plug in 3, it's going to give you the area from 0 to 3. So if you plug in 3, it's going to give you 27 over 3 is 9. That's this area right here, okay? If you plug in 1, it gives the area from 0 to 1. Just this area right here, okay? So you're like, okay, fine. But what if I don't want the area from 0 to a number? What if I want the area between any two numbers? Okay, like say 1 to 3. That would be all this area. Well, how could we do that? Let's just think geometrically. What would be a good strategy? If we can find the areas from 0 to any number, could we use that to somehow find the area between any two numbers? Couldn't you just do the big area first and the little area second and subtract it to get what's in between? Right? That's the strategy. I'm going to subtract. A3 minus A1 gives you 8 2/3. That's the area under parabola from 1 to 3. And we're going to do this all the time. And this is why when you integrate, you usually plug two numbers in, a bottom limit, top limit. You plug in the top first, the bigger one first, plug the bottom one in second, and you subtract because of this. Okay? Now, just to make it a little more complicated, is this the only function whose derivative gives you x squared? Nope. Can you think of some? What are some other functions that we could have written for the area? How about x cubed over 3 plus 5? Wouldn't that give you the same one? That'd give you different values here, right? But it would still give you the same value between any two numbers, right? So we're going to rely on this idea all the time. Okay, in fact, you could do x cubed over 3 minus 2. I mean, x cubed over 3 plus or minus any number will work. Okay, so when we integrate, this is the symbol we're going to use for integrating. X squared dx, this is a Greek letter. I think it might be sigma, which we often use in math and even science classes to represent the sum of a bunch of smaller numbers, which is actually what we're doing here. I'm going to get more into it. But this right here, the x squared, that's like the height. Like what we're going to be doing is we're going to actually be thinking of these as tall, thin rectangles. Tall, thin rectangles. When we cut this out, this is how we're doing it. Tall, thin rectangles with a base and a height. My pin's running out. Base and a height. The base is going to be a small change in x. The smaller, the better. And we're going to call that delta x. The height is going to be whatever the y value of the curve is. Right? This is going to be whatever the y value of the curve is, f of x. In this case, it's x squared. So when we write an integral this is the height of the rectangle. This is the base of the rectangle of a thin, skinny one. And this means we're going to add a bunch of them up. Okay? And then we're going to get x cubed over 3. But then we always are going to write plus c because, look, it could have any of these numbers, right? That's called the constant. That's the constant of integration. So you got to have that. You need that. All right? But it's kind of like we're looking at this like a bunch of thin rectangles. Okay? And rectangles aren't going to perfectly get the area underneath here. There's going to be a little bit of jagged rectangle above or below, but the more of them you do, the better it is. And if you take it to infinity, it's going to be perfect. It's going to give you the right answer. Now, this is also Greek letter, which is delta. Looks like a triangle. And it's usually for something that's really small. Okay? So we're using this for these thin slices. Okay? We're going to come back to this. We're going to come back to a lot of this. I'm kind of giving you a quick overview of a lot of the stuff, and then we're going to get more detailed. Now, we are going to, if you know your derivative rules well, then the antiderivative rules shouldn't be that hard because they're the same rules backwards. But, at first it takes a little getting used to. But you kind of, to me, the way I usually remember these is by remember how to do them forward. So you essentially ask yourself, what would I take the derivative of to get x to the end? You say, well, this is the power of what we just talked about. You bump it up 1, divide by the new exponent. Instead of multiplying and subtracting from the exponent, you add to the exponent and then divide. And of course, you need the plus c. If you don't write that on your next test, you're going to lose points. Lots of points. Trig. What do you take a derivative to give you cosine? And you say, oh, that's sine, right? Now be careful. It should be positive or negative. Positive or negative? What do you think? Positive or negative? Some people go, oh, well, if it's cosine, it's going to be negative. Nope. It's positive because the derivative of sine is positive cosine. Now, what do you take derivative to get sine? You say, oh, cosine. But the derivative of cosine actually gives you negative sine, so we need an extra negative to make that other negative go away. Okay, so anything you take if anything you integrate involves co in the answer, it's going to have a negative. Okay, secant is tangent squared. Cosecant is negative cotangent. Secant tan is secant. Cosecant cotangent negative cosecant. E to the x is e to the x. It's its own derivative, its own antiderivative. B to the x is b to the x divided by natural log of b. Because if you take the derivative of b to the x, you get b to the x times the natural log of b, which we don't want right here, so you got to divide by. It's just a number. 1 over x is going to be natural log of the absolute value of x. 1 over 1 plus x squared, that's inverse tangent. That's one of those inverse trig ones. 1 over the square root of 1 minus x squared is inverse sine. If you wanted to, you could do, or you could even say negative cosine inverse, because the derivative of inverse cosine is the same exact thing, but it has a negative in front. But we usually don't use that one. Okay, now all these answers have C's in them, right? So are we ever going to have answers that don't have C, or where we can find what C should be? And the answer is yes. Those are called initial value problems. So here I have a derivative, but I have an initial value, some value on the original graph. Okay? And this helps find C. Okay? So, let's see. The original function, which we would get by integrating the derivative, right, which we get by integrating x plus sine x. What's the antiderivative of x? What would you take the derivative of and just get x when you're done? Well, better involve x squared, right? Because you have to drop it down by 1. But there's going to be a 2 in front, so we've got to divide by 2. Bump it up 1, divide by the new exponent. This one's going to be minus cosine. plus c. Okay. Now what we can do is we can say, let's use this initial value. If I know any xy pair for my function here, then I can plug the x and y in here, and then I should be able to find c. So if you plug 0 in, you get 1/2 0 squared minus cosine of 0 plus c should come out to 3. Add 0. This is 1. So if you add 1 to both sides, you get c equals 4. Okay. So now we could rewrite it. Our function f of x equals x squared over 2 minus cosine x plus 4 is now the answer, specifically without a plus c. If you don't have an initial condition, then you just leave plus c there. Now, here's just something a little extra challenging. How would you integrate this one? Like, we don't, if we look at this list up here, we didn't do a reverse product rule. And this looks like some kind of product, but could we somehow get away with it without doing a product rule? Think about it. Pause the video. Think about it. My solution is, let's change that to an exponent. Let's distribute this in here. And we can, because there's no power out here. And using rules of exponents, it's going to be x to the 3/2 plus 2x to the 1/2. Got to write the dx. You got to put these parentheses around here. If there's multiple terms, you have to put parentheses. So now we should be able to do it. These are two separate power rules. So we're going to bump it up by 1 and then divide by the new exponent. Or if it's a fraction, multiply by the reciprocal plus, I'll show you on this next one, x to the 3/2. And instead of writing divided by 3/2, we could write times 2/3. That's the same thing, right? That's the same thing. Plus c. I don't have an initial value this time, so my answer is just going to have a c in it. So this is going to be 2/5, right? After you divide by 5/2, the same as times 2/5. X to the 5/2 plus 4/3, x to the 3/2 plus c. And that's your answer. Now today's assignment, there's two things. There's a book assignment, and then there's the Cinderella Sasquatch project. So the Cinderella Sasquatch project, see if I can find a picture for you. I want you to take like a sheet of paper. For most of us, a standard sheet of paper might work. Unless you have a really big foot, then you might need a bigger piece of paper. And I want you to trace either the output of your shoe or your foot. Okay? The outside of your shoe, outside of your foot. Okay? So you can kind of get like a footprint. I want you to try and find the area of your foot, 1 foot, and also the area of your hand. So you can put your hand on here, trace around your hand, and then close it off. Let's see if you can find the area of your hand. Now, the way I want you to do it is I want you to cut it up into different kinds of shapes. I want you to try and use like maybe 10 shapes or less, or 10 measurements if possible. So you can get better estimates for the area worse depending on how you attack this. You could use circles or rectangles or triangles or trapezoids or any kind of shape that you can find the area of. You can use a ruler to measure how long the dimensions are. And you can do it any way you want. I mean, here's some rough ideas, but I want you to get creative with it. And you could even color it or decorate it or whatever for fun. It is an assignment, okay? Show the work for your calculations. So whatever shapes you used somewhere else on the paper, or a separate sheet of paper, or on the sides of the outside the foot, show your calculations and your final estimate. So I want to see your strategy, and then I kind of want to see the work you did to get your final answer. And so the Cinderella Sasquatch part is like Cinderella might be like the smallest. She had notoriously small feet, right? Her wicked stepsister's feet couldn't fit into it. Sasquatch is a big big animal. So maybe the biggest foot in the class will be the Sasquatch winner, unless if it's embarrassing to you, that's fine. You don't have to. I won't announce it. But anyways, it's just kind of a good. Just a good little project to get, it shouldn't take a ton of time, but it's kind of a good way to exercise your understanding of the approach we're going to be taking this chapter to find the area in complicated curves. Okay. We're going to use all kinds of different shapes. So you're free to use whatever kind of shapes you want, but that's also part of it. So your hand and your foot, your hand with barefoot, or your hand with the shoe, or your foot barefoot, or your foot with a shoe on, and then your hand also. Okay, make sure you put your name on it somewhere, and then try these problems. They're all odds. They're all in the back of the book, and we will continue to learn about integrals the rest of this chapter.